Hi everyone, I'm Charlie Claremont, Technical Director at Synaltic. Today I'm going to tell you how we transformed a real-time flight simulation system into a modern analytics platform, automatically managing over 1,000 columns while respecting a 5-millisecond constraint. Spoiler alert, Apache Iceberg was our secret weapon. I'm Technical Director at Synaltic, a data consulting company founded in 2004 and specialized in data architectures. For over 10 years, I've been helping organizations with their data transformations. Imagine a VHS cassette versus a digital video file. With VHS, you can watch it, but impossible to ask, show me all-night scenes. The digital file has metadata, duration, chapters, subtitles. Our client, a leader in flight simulation, had exactly this problem. Their simulators recorded flight sessions, but in a proprietary format, like digital VHS tapes. Impossible to extract altitude at the 23rd minute, or how many times did the pilot exceed maximum speed. This data is available during training session, in live, but not queryable. Our mission, move from analog to digital. The existing architecture, a federated simulator with multiple systems communicating via a C++ databus. Flight data is recorded, but in a proprietary format designed to be replayed in the simulator, not to be analyzed. The business needs were twofold. First, real-time analysis during simulation. Imagine an instructor seeing alerts when the pilot makes a mistake. Second, cold analysis. Compare a pilot's performance over 6 months, identify patterns, feed machine learning models. 3 major technical challenges. First challenge, cross-language serialization. The C++ application produces complex objects. We need to serialize them for Kafka, then exploit them in SQL. XML? Too verbose. Avro? Too rigid for our evolving schemas. We chose XML to JSON via a streaming flow. Second challenge, the 20-millisecond cycle. The simulator produces data every 20 milliseconds. That's 50 times per second. If the Kafka send blocks, the entire simulation freezes. Unacceptable for a pilot in the middle of an exercise. Third challenge, we were navigating in uncharted waters. Actual data volume? Unknown. Schema stability? C++ objects evolve with product versions. Structure complexity? Objects nested 6 levels deep, with sometimes over 1,000 attributes. Here's the architecture we built. First layer, a C++ injector sends to Kafka Red Panda. Why Red Panda? It's Kafka, but written in C++ -P50 latency of 5 milliseconds versus 10 to 50 milliseconds for classic Apache Kafka. Configuration, 150 topics for 11 entity types, 10 partitions for parallelism, LZ4 compression. Second layer, Apache Flink consumes these topics, transforms XML to JSON, and does 2 things simultaneously. Stores raw data in min.io as archive, and republishes JSON to Kafka with a staging prefix. Third layer, the Kafka Connect Iceberg sync connector consumes JSON and writes to Apache Iceberg, Parquet format, Nessie catalog for versioning. Fourth layer, Dremio as query engine, exposes Iceberg tables in standard SQL. Performance target, less than 20 milliseconds. Measured result in production, P50 latency at 8 milliseconds, P99 at 18 milliseconds. Target achieved. The key was tuning the C++ producer, fast LZ4 compression, light 5 milliseconds batching, and simple acknowledgement without waiting for complete replication. The simulator was never blocked. First approach, be proactive. We try to define Iceberg schemas in advance. We parse XML sources, generate DDL, create tables manually. Result, complete failure. As soon as a new column appeared in the C++ code, and that happened every week, our inserts crashed. Type change? Error. Nested structure too deep? Error. The fundamental problem, trying to freeze a schema when the source application evolves continuously, is condemning yourself to breaking in production. We needed a radically different approach. The revelation came from 2 Apache Iceberg sync connector parameters, auto create enabled and evolve schema enabled. Basically, let the connector create and evolve tables automatically. Concretely, here's what happens. At T0, the first JSON message arrives. The connector detects there's no table. It creates one with 47 columns based on the JSON. At T0 plus 5 minutes, a new fuel_level field appears in the JSON. The connector detects the new field, launches an alter table add column, all in less than 100 milliseconds without human intervention. After 1 day in production, over 1,000 columns managed automatically, with structures nested several levels deep. It was mind-blowing. The schema management nightmare transformed into a non-issue. Concrete example with the CSR aircraft table. About 100 columns at root level, the object's direct attributes. But the object contains nested structures. Spatial contains position, which contains latitude, longitude, altitude. Spatial also contains velocity, with x, y, z, and so on for several levels. In total, over 900 columns in nested structures. Apache Iceberg's Parquet format handles these nested columns natively. They're flattened for querying. In Dremio, we access these deep fields with standard dot notation, spatial.position.latitude. Transparent for SQL users. Why does it work so well? 3 technical pillars. 1. Separated metadata architecture. Parquet data files are immutable. Manifests list these files, and metadata defines the schema. When we add a column, we only need to update the metadata file. No need to rewrite the data. It's instantaneous. 2. Schema evolution is built into the Iceberg spec. Add a nullable column? Supported. Rename with an alias? Supported. Widen a type? Int to long? Supported. 3. Parquet format natively handles nested structures. A JSON nested 5 levels deep becomes flattened columns for querying, but stored efficiently. One regret though, the variant type. Some fields in our JSONs contain other JSONs serialized as strings. Currently, it's stored as an opaque string in Iceberg. You have to parse manually in queries. The variant type, available in Snowflake and in preview in Databricks, stores semi-structured JSON natively queryable. For us with 1000 columns, some of which are JSON within JSON, this would be a game changer. The flip side of real-time, small files. With a commit every 60 seconds, 1 hour of simulation generates 600 small Parquet files. Negative impact on read performance. Solution: automatic compaction. Dremio launches an optimized table job 1 hour after each simulation ends. 600 files become 20 optimal files. Then vacuum table cleans up old snapshots beyond 7 days. Automated, transparent. Results on the technical side: ingestion latency at 8 milliseconds, well below target. Over 1000 columns managed automatically. 0 manual intervention on schemas in 6 months of production. Queries on complete data in less than 1 minute. But the real impact is on the business side. Real-time analysis. Instructors now have live dashboards, alerts when a pilot makes a mistake. Automatic performance scoring. Historical analysis. We can compare a pilot's evolution over 6 months, identify which scenarios generate the most errors, optimize training programs. And machine learning. With all the history accessible, we train AI models to make personalized recommendations, predict risky behaviors. This pattern isn't specific to flight simulation. All industrial companies with C++ legacy have the same need. Transform their real-time data into analytical assets. Manufacturing with SCADA sensors, automotive with CAN bus data, energy with turbine monitoring, aerospace with telemetry, same problem. The architecture we built is reusable. Keep the working C++ application, add a Kafka export layer. That's a few hundred lines of code, then Apache Iceberg as a modern lake, and a query engine on top. Benefits: no need to rewrite the business application. Data becomes historized and queryable, and you have the foundation to do AI and machine learning. 3 key lessons for industrial companies wanting to get started. Lesson 1. Don't rewrite the existing. Your production C++ application works. It has value. Keep it. Simply add a Kafka export layer. That's less than 500 lines of code. Sidecar architecture. You plug in the data without touching the application core. Lesson 2. Embrace schema uncertainty. Don't try to freeze your data model. It will evolve, that's certain. Use Apache Iceberg's auto-creation and schema evolution capabilities. The connector is smarter than you. Let it work. Lesson 3. Think hot plus cold architecture. Kafka is your fast buffer. You keep a few hours or days for real-time analysis. Apache Iceberg is your analytical archive. You keep years. Flink and Dremio are the bridges between the two. In conclusion, Apache Iceberg doesn't replace your business applications. It augments them for the data era. It transforms real-time systems, excellent at their job, into modern analytical platforms. The near future is exciting. The variant type will massively simplify semi-structured data management. Apache Flux is emerging as a Kafka alternative, optimized for tables. Iceberg REST catalogs will make deployment even simpler. Resources: the Apache Iceberg website, of course, our Synaltic white paper on the complete architecture, and C++ example code we've open-sourced. Thank you for your attention.